Welcome back to part 2 of my data logger project video. I needed to create an enclosure to hold an LCD to display water pressure data. A rotary encoder dial with push to select was included to provide some basic user input. Part 2 shows how this was done. It isn't a premier aspect of the project, but might be of interest to some. Previous videos chronicled my aluminum box project designed around fitted top and bottom parts. This design worked well for my attic vent and sensor control PCB and my evaporation cooler's 24-volt thermostat interface. After some tinkering, I came up with a better enclosure design for this project, one that is less sensitive to absolute dimensional errors and uses a 3D printed component panel. Per usual, there is a blog link in the description to more information, drawings, models, and details. Just a brief reminder here on the project box. This was the original design. It was a two-part box with a base, a bottom, and a fitted top. Videos on that were published. This box works out pretty well. The only hassle with it is it's fitted, so you got to be real careful with the bending and the dimensions. So there were a lot of toads kissed before I got to the prints. I came up with a different design here. I was thinking in terms of creating a frame like this from two identical parts. One could be flipped over so you get a mirror image, and the idea was you had a tab that was created here that would fit in and you get this kind of an effect. This one turned out pretty well. I didn't cut back quite far enough on the miter here, so you can see what's going on with that. The fit's okay, but if you look in here, you'll see it's not quite fitting right. So I had to play around with that a little bit. But the idea with this design was you create a frame and then you have a flat surface that you can put a printed component plate on, and then you can just close the back in with a flat piece of aluminum. So this was actually easier to work with components. So that was that, and here's the piece, the first piece I bent, and this one came out a little bit better on the miter, but like I said, I had problems. I couldn't even use this. I had problems with this miter. I didn't set it back enough. So that one was kind of went south, and this one here was kind of the same thing. And I was working with it, and you'll notice here this is quite a gap, a pregnant gap in here. That notch that you cut, and I'll make a flat piece and I'll make one of these and you can see what's going on with that, but that's real critical. Just like 5 or 10 thousandths too far and you're going to get this big gap. But if you put a cover on that, you don't really see it. So in playing around with this, I thought about simplifying it even more. So I came up with this design, which actually is even better. And what it does is it eliminates the miters on the ends, and there's only one in the middle. And these are test pieces. It's not complete, but we can go in here and we can look at the fit. This fits really well. You can see it here in the back. Comes out nice. You can put a couple pop rivets here and here, and this becomes your corner. The first one I did was this side here, and you can see what happened here. I screwed it up. There's a big, huge gap in here. I made a measurement error when I did the notch, and then the width was messed up, and it just didn't work out too well. So this side here worked out really well, and this is actually a perfect fit. And the idea with this is once you do your setup, you're making two identical pieces. So you can notch two pieces the same way, you can cut the width two pieces the same way, you can cut the length two pieces the same way, and the absolute accuracy isn't that tight, and as long as the relative accuracy between the two pieces is pretty good, and that's a little easier to obtain, then you're going to get something that fits pretty well. And then what happens is when you build the box, then you can take a measurement on the outside and see what that is, and then you can base your component panel dimensions on that and your back dimensions on that. So that's kind of how that was done. And what I'll do next is I'll go ahead and cut the flat plate out, show the drawing, the flat layout, do some notching, do some bending, just so you can see how this part of the box or the frame was made for the LCD and input enclosure. Here's the drawing for the flat layout of the frame for the LCD and input module. Couple quick comments. This is a pretty simple part, and it's generated from FreeCAD, the unfold tool in the sheet metal workbench. There's a notch here and a little small notch here that you need to make, and then there's the V notch here. This articulated part of the drawing here, probably ignore that. It's modeled accurately, but in reality when you make this piece, it doesn't really matter, and it's awful hard to fabricate this unless you're going to laser cut this piece out, which I don't have a laser cutter, so I've got to work with my notcher and my shear. That's all I've got. So this has been all spec'd out. There's a link to the blog in the description, which will get you to this drawing, get you the model. Here's an isometric of the part. So let's go ahead and make this part. Okay, I blanked out this part. I didn't show it. It's not that exciting. And I put some reference lines on it. The drawing calls out a width of 2.023. I converted to inches. So let's just measure this and see what we got. I think I got the width pretty good. So we're looking, I don't know if you can see that, we're looking at 2.0215. It's pretty good. 2.022. And the length is called out at 10.147. So let's see what we got for the length. So let's see here, get this lined up. 10.144, 10.145, we did pretty well on that. So that's the flat rectangular piece. And I went ahead and I did the notching per the drawing, and that basically comes down 20.92 millimeters and then goes over 9.5 millimeters for this notch, and then there's another little small notch which is 1.92 in, and then it comes down, let's see what the drawing says, 13.02. So I just did this. So you set up the notcher, you notch it, you flip it over, you notch it again, you reset up your notcher for this notch, you notch it and you flip it over and you notch it, and then you do this obviously for a second piece. So they all come out the same. Here's my bend line, and that is indicated here at 4.880 up from the bottom, and then here's my notch. So what happens with this is the bend center for the sides, and the bend allowance is going to be 0.138 inches. So that's half of that above this line and half of that below. So this is where you got to be real careful. If you notch right to that line, you're going to get kind of a pregnant miter gap in here. So we got to, I'll go over and I'll do the notch and we'll see how it turns out. But you got to be real careful with that. And as I had mentioned, 5 thousandths on this makes a big difference on how this miter is going to fit together. So that's the story with the piece. We got just the notching left here to do, so I'll go over and we'll take care of that. And then we bend out the part and see how it turns out. Okay, we got the notcher set up here to take care of this V-notch on either side. So we'll go ahead and do that. Hopefully we got it right. Okay, so there's our notch, which will be our mitered corner. Okay, we took the masking off. Let's fire up the press brake again. We're set for a 1/2 inch bend. We checked that, so it should be pretty good. Our dies are nice and clean. So let's bend this out, see what happens. We can hit it again. Go to the other side here. Hit that again. Okay, so there's your piece. As you can see here, I went in a little bit too deep, so we're probably going to have a little bit of a gap, maybe more than we'd like, on these mitered corners. It's not serious, it's a little small detail. If you're fussy about it, you might not like it, but at least this way we can get, there'll be enough room to make a 90-degree bend. So I got to change the dies out because we got to get in between here. I did a video on sectioning off these dies specifically to deal with this kind of a situation where you have a box and pan situation. So let me change out the dies, and we've got 2 more bends that we got to make. All right, I changed out the upper die. We got a 1-inch die section here. It's kind of funky, but we'll cycle the machine once. We're still going to make a 1/2-inch bend on this tab. We got to be careful here not to screw this up. Okay, there's our 1/2-inch bend. This bend here, we got to adjust the back gauge, so I got to crank on it for a little bit. So let me go ahead and set that up, and then we'll finish this piece off. Okay, the back gauge setting was called out at 4.88, so I did that setup off this end here. So we got to be really careful that this doesn't slip. So we're gonna put this in here. See if we can get it right so we don't screw it up. Okay, there it is. That's the last bend. This isn't too bad. I'm kind of happy with how that came out. I suppose we could have tightened that up a little bit, but actually I thought it was going to be kind of worse than it turned out to be. So let's go over and take some measurements and see how well we did. Okay, we got a V-block in here, which is handy, so we can take a look and see what's going on with this. This is pretty close. You can see it's wiggling a little bit, so we can kind of make a slight adjustment in that. That's kind of one of the advantages if this miter is open a little bit. So there we go. That's a nice 90-degree bend we got there. So the next thing we can do, I made this gauge piece. We can check the corner, and that looks like it's dead nuts right on there. Let me see if I can get my hand out of the way so you can kind of see how that fits right in there. And I just got a little tiny gap in there, which we want, and then we're kind of nice here where the tab goes underneath. We're going to do some pop rivets in there. So there, you could see how that. Hopefully you could see how that fits in there like that. So this is actually just half the frame. So we would have made 2 pieces identical like this. When everything is set up, we just cut everything twice, and we come up with 2 pieces that are like this with a good relative accuracy, and then those pieces will fit together and then make a square frame. And I'll show you the finished frame, what this turns into next. Okay, here's the finished LCD and input enclosure that we saw in part 1. And you've got the frame here, which we just saw. There's 2 pieces that make a frame like this. So let's see here. Hopefully you can bring this in a little closer here so you can kind of see that corner there, how that got a couple pop rivets in there. You can see how that fits right there. And it's symmetric. There's another 2 pop rivets on the other corner. So that's kind of how this works. And again, the advantage of this was I was able to make a flat 3D plastic printed component plate. And then the back is real simple. It's just a square piece of aluminum. I put some rubber feet on there. So that's kind of how this all went together. It turned out pretty well. And one of these cables feeds the LCD, and the other cable takes care of the rotary dial. So that's the finished case. Here's a peek inside the box with the bottom removed. You can see the corners and how two identical frame pieces fit together. The 4x20 LCD is on the right and the rotary encoder is on the left. Videos and documentation are out there detailing the rotary encoder dial project. The front and back of the box are flat pieces. Let's take a look at how the 3D printed component plate was made. I did a layout in LibreCAD which shows the 127mm box frame and 12.7mm sides. Then I placed the LCD bezel hole and mounting screws in position. The rotary encoder mounts with a single screw, but its PCB must be accounted for. The hole pattern on the perimeter served as a template for the back cover. You can print these out, cut with a razor, and get pretty good accuracy for locating holes. I drilled the frame out with a number 36 drill, then tapped to 632 in 16 places. I removed all the non-essential lines to create a layout for the 3D printed component plate. This gave overall dimensions and holes. Using the draft workbench, I imported this into FreeCAD, converted it to a sketch, then padded the part to 4mm. If I did this again, I'd go just 3mm. The print used white PETG and ran 2 hours and 45 minutes. Give the bezel hole 0.5mm of clearance. I also printed 4 spacers 4mm tall to mount the LCD. You'll need to do this to clear the LCD's backlight injection point. Here are some excerpts of the print. Summarizing, I needed a display device to monitor pressure. I included a simple input device for flexibility. Both these devices required mounting. A perimeter frame-based box design worked the best. 2 identical aluminum parts bent into corners provided the frame. This allowed a flat component plate and back to close in the box. The component plate could be easily printed on a 3D printer. The back was a simple square piece of aluminum. Wiring exited the side through a grommet. This worked well for me. Next, I'll cover the Nano V3 PCB and how that fits into the project. The final goal is creating a time-stamped CSV file that I can import into a spreadsheet. I'll cover this in upcoming videos.